Good day, students, and welcome to part 2 of the process of factoring and solving polynomials using the rational roots theorem and the fundamental theorem of algebra. So we're going to be answering these 4 parts on the upcoming problem. So part A says that for each given function, we have to use a corollary to the fundamental theorem of algebra to state the maximum number of complex roots, real roots, which is the same thing as intercepts, and terms of the graph of the function. In the B part, we have to use the rational roots theorem to list all the possible rational roots. Part C, we have to write the polynomial as a product of linear factors and find all the zeros. And then lastly, we have to sketch a possible graph of the function. All right, so the problem that we are going to be dealing with is, let's see, is x to the fourth All right, so the problem is x to the fourth minus 3x, plus 2x to the third minus 3x squared minus 20x minus 24 equals 0. All right, so that's what we're going to be dealing with. All right, so part A, let's see the maximum number of complex roots, maximum number of complex roots. So using the corollary to the fundamental theorem of algebra, we know that if we look at the degree of the polynomial, it can tell us the maximum number of complex roots. So since the degree is 4, we know that it can have a maximum of 4 complex roots. Okay? Now how about the maximum number of real roots? Real roots, or you can call them the x-intercept. How many times, what's the maximum number of times it can intersect? A function of this nature can intersect the x-axis. It's exactly the same number, is the same as the maximum number of complex roots. Okay? This is a case where all the roots are real. Okay? But it could be the case that they're all imaginary. But if they're all real roots, then we're going to have 4. So the maximum number of real roots that this function can have, a function of the 4th degree can have, is 4. All right? How about the maximum number of turns or changes in direction? Well, it's always 1 less than the degree. So if you look at the degree here, or the maximum number of complex roots is 4. So the maximum number of turns that the graph of a function of the 4th degree can have is 3. Okay, so you just subtract 1 from the 4th power. All right. Now, let me give you a graphical illustration to see, to understand this result. So let's say we have a 4th degree polynomial function. If we graphed it, it could look something like this. Okay. If it's positive, it will open up. If it's negative, it will open down. All right. This is a graph where it has a maximum number of turns. Okay. So if it has a maximum number of turns, what is the maximum number of x-intercepts it can have? So case number 1, what if it's been right here? If that's the x-intercept, then in that case, you have absolutely no real roots. They're all going to be complex, they're all going to be purely imaginary. Now, what if you have it in such a way that it touches those 2 points right there? In that case, you have exactly 2 real roots, which are 2 double roots. Okay, so you have 2 roots. Now, what if you have it in this situation, if it goes like this? How many roots do you have there? You have exactly 4 real roots, if this were your x-axis. So 1, 2, 3, 4, if this is your x-axis. All right, so these are the possible cases. You can clearly see that if this graph had another turn, it will result in there being 5 roots, which is a violation of the corollary to the fundamental theorem of algebra. So if the degree is 4, it can have at most 3 turns or changes in direction. Okay, and then it could also have 3 roots also if the graph looked something like this. Let's say you have a situation where it goes like that and like that. Okay, if the graph looks something like this, which is a 4th degree polynomial function, and the x-axis went through like this, how many How many roots, real roots do you have here? In this case, you're going to have a double root right here, and then another root, and then you have another root here. So you can have, you see, you can have either 0, 2 roots, 3 roots, or 4 roots. And you can have exactly 1 real root if you have, let's say the x-axis goes through the point like this, something like that, and you have exactly 1 root. So you see all the possible scenarios that you can have. But the maximum number of real roots you can have is exactly the same as the maximum number of complex roots, which is 4. Okay? And the terms cannot be more than 3. All right, let's take a look at the B part. In the B part, we're to state the number of possible rational roots. Okay? List all the possible rational roots. So to find out the possible rational roots, we know what the rational roots theorem says, that if P over Q is a rational root, it's a rational root, then P is a factor of the last term, and Q is a factor of the first term, is a factor of the coefficient of the first term. Okay, the last term is a constant, and the coefficient of the first term is what we'll look at when we're determining if Q is a factor of the first term. All right, so there goes the rational roots theorem. So in order to find all the numbers that satisfy this, what we're going to do is we're going to list them. Okay, so normally the possible rational roots are going to be plus or minus P over plus or minus Q. Okay, some people like to write it as plus or minus C as a constant over plus or minus A for the first term, or you can say plus or minus factors of the first term. Let's just apply the problem. In this problem, the last term is 24, so plus or minus factors of 24 divided by plus or minus factors of the first term, in this case, is 1. Okay, factors of 1. All right, so what is this going to look like? It's going to look like, let's list the factors of 24, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and then plus or minus 24. All right, so those are all the factors of the numerator, the last term, which is 24, over the factors of the coefficient of the first term, which is plus or minus 1. Okay, so let me go back to the problem. So there's an invisible 1 right here, as you all already know. So this one is going to be our Q, or last term, factors of that, and then this one right here will be our P. Okay, factors of that. All right, so what are the possible combinations we can have? All you do is you take one from the top and one, and then pair it up with the bottom, and then you just pair one from the top with the bottom, and then you go on and on like that. This is easy because you have only one term in the bottom to pair up the numerator factors with. So that's going to yield, this is going to give us plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus 6 over 1, plus or minus 8 over 1, plus or minus 12 over 1, and then we have plus or minus, over here, plus or minus 24 over 1. Okay? So this is nice because when you divide, you get only 1, but it's not always the case. Sometimes you have much more complicated problems, all right? So this one, our possible rational roots. So possible rational roots. Roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and then plus or minus 24. Okay, so these are the possible rational roots that we have. 1, 2, 3, 4, 5, 6, 7, 8. So we have 16 of them, positive and negative together. Okay, so there you have it. All right, let's move on to part C. Part C, we are to write the polynomial in as a product of linear factors. So let's do that. So what we'll do is we are going to use synthetic division to determine what the factors are. So if I set up my synthetic division bars, I'm going to extract the coefficients from my polynomial. So they are going to be 1, 2, negative 3, negative 28, and negative 24. Okay? So I'm just extracting all the coefficients of my polynomial. So this is 1, 2, negative 3. Let me underline it so you can see. So you extract this. You have to make sure that the degrees are in descending order and no degree term is missing. Okay, if a degree term is missing, you're going to have to put a placeholder to fill that spot. So nothing is missing here. We have 4, 3, 2, 1, 0, so we're good to go. All right, so what we're going to do is basically test all our possible rational roots. If we have a rational roots that yields a remainder of 0, then it is a factor, and then we'll go on from there. Okay, so let's start with negative 1. All right, synthetic division, put a 0 there because there's nothing. To do the synthetic division, the process is you add downwards and you multiply across. Okay, so when you add down 1 plus 0 is 1, multiply across, negative 1, add down, 1 multiply across, you get negative 1, add down, negative 4, multiply across, you get 4, you add down, you get negative 24, multiply across, you get 24, add down, you get 0. This is excellent. Since you have a remainder of 0, that means that this is a factor. This is a root. Okay, so now we're going to write down the depressed polynomial, and also this as a factor of the original. So we have x, since this is minus 1, you write the opposite, x plus 1, times, now the depressed polynomial, we're going to have x to the third. Is always going to be a degree less than the original. The original was a fourth degree, so this will be a third degree. Okay, so x to the third plus x squared minus 4x minus 24. All right, we have to write this as a product of linear factors. This is a cubic, so we have to break it down. We're going to apply the same process to factoring this again. So we need to list all the possible rational roots for the for this one, and then do synthetic division. Okay, so we're going to write down the factors of 24 divided by factors of 1. All right, plus or minus, plus or minus. All right, so we've done this before, so we already know what they are, right? We had them up here, so we can use this as a guide. So we know that the factors are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and then plus or minus 24. Okay? So if these are a factor of the original, they're also going to be factors of a depressed polynomial too. So it just carries over. All right, so let's test negative 1. Okay, so you don't have to list this again because you already listed it before, but I'm just writing it so that you can see where I'm getting my factors from. All right, so let's go ahead and test negative 1 on the depressed polynomial. We're working on the depressed polynomial here, okay? So take out the coefficients from this or just extract that. We have 1, 1, negative 4, negative 24. Okay, test negative 1. Start with a 0. Add down, multiply across. Add down 0, multiply across 0. Add down, multiply across 4. add down negative 20. This is not a factor anymore. Okay? Alright, let's try, how about we try positive 1 and see if that works. You never know, we just keep trying until we get one that works. Alright, let's try positive 1 to the same depressed polynomial. 1, 1, negative 4, negative 24. Let's try 1. For the 0, add down, multiply across. Add down, multiply across. Add down, multiply across. Add down, not 0. So this is not a factor because you do not have a remainder of 0. Okay? Alright, let's try, how about we jump? I'm going to jump to positive 3. Okay? Why am I jumping to positive 3? Because I'm cheating. I know that it's going to work, so ideally you would try 2 and negative 2 and then 3 and negative 3 and positive 3. Keep trying until you get the one that works, okay? So I know positive 3 should work, so we're going to rewrite the depressed polynomial. 1, 1, negative 4, and negative 24. Alright, to the 0, add down, multiply across. Add down, multiply across. Add down. You have, and then multiply across, 24. Add down, you get 0. Okay? So you see that this is another factor of the first polynomial or the original polynomial. Okay, so let's go ahead and write it down. So we're going to have the first one was x plus 1. So we have x plus 1, x plus 1 times x plus 3. Actually, x minus 3. You always have to do the opposite. X minus 3. And the depressed polynomial, x squared plus 4x plus 8. Okay? Now, to do this depressed polynomial, to factor it, or to find the zeros, we can try factoring using the x game. So let's try that and see what happens. So if we make the x, AC goes on top, B goes on the bottom. AC is 8, B is 4. Let's see. 8 times 1, no. 4 times 2, absolutely not. So this is prime. So we can't use the x game. So this fails. So what we're going to have to use is the quadratic formula to find out what these zeros are. Okay? So the quadratic formula, we know what that is. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, so this is what we're going to employ. All right, so let's go ahead and do it. So we're going to need ABC. In this depressed polynomial here, a is 1, b is 4, and c is 8. Okay, so let's plug all this into the quadratic formula. We're going to have x equals negative b, which is 4, plus or minus the square root of b squared is 4 squared, minus 4 times a, which is 1 times c, which is 8. And then that entire expression divided by 2a, or 2 times 1. Okay? All right, let's go ahead and simplify this. So if we do, we're going to have negative 4 plus or minus the square root of, 4 squared is 16. 4 times 1 times 8 is 32 over 2. Okay? That simplifies further into negative 4 plus or minus the square root of negative 16 over 2. So that becomes negative 4 plus or minus square root of negative 16 is 4i over 2. And then that gives us the final answer. X is equal to negative 2 plus or minus 2i. That's if you divide these two by the 2 downstairs here. Okay? So if I want to write this as a product of linear factors, I'll just set it equal to 0, and I'll have x minus 2 plus or minus 2i is equal to 0. Okay? So if I want to write it in split form, I'll write x minus 2 plus 2i times x minus 2 minus 2i. All right, so this is expressing this prime quadratic as a product of linear factors. Okay. All right, so let's go ahead and write it down here. So expressing this as a product of linear factors, we have x plus 1 times x minus 3 times x. Let's go down. I forgot already. X minus. Well, actually, this is a minus, so this has to be a plus. If I move it to the other side, this is going to be a plus. Because you add 2 and then you do the plus or minus 2i and then move it to the other side. Okay? So you do the opposite. All right, so x plus 2 plus 2i and x plus 2 minus 2i. Okay? So let me go over how I did this again. So remember, if you want to set it equal to 0, first of all, you will, let me do that over here. So you have x is equal to negative 2 plus or minus 2i. You can add 2 to both sides. So you have x plus 2 equals plus or minus 2i. And then if you add plus or minus 2i to both sides, you're going to have x plus 2. If you do the addition becomes subtraction minus 2i. If you do the subtraction, it becomes positive. So adding plus or minus 2i to both sides is going to be exactly the same. Plus or minus 2i equals 0. Okay? So and then when you split it, you have these two factors right here. All right? So that's how I was able to come up with this expression. Okay, so now we have it written as a product of linear factors. So we're going to now state the zeros. So what are the zeros? To state the zeros, you're going to set each factor to 0 and solve, right? So x plus 1 equals 0, x minus 3 equals 0. These two, we've already solved them for what they are. It's negative 2 plus or minus 2i, so we don't have to bother solving them again, okay? So your zeros are going to be, we have 2 real zeros and 2 imaginary zeros. If I subtract 1, I get the first one. Add 3 to both sides here, I get the next one. And in my imaginary zeros, I have 2 minus 2i. And let me make sure I have this right. Minus 2i as the first one. And then minus 2 plus 2i is the second rational imaginary root or 0 I have for the original function. Okay, so there you have it. Okay, now that we have the solution, we know that we have 2 x-intercepts and 3 terms. Okay, so we're just going to draw a possible graph. This is not 100%, it's just a possibility. This could be a solution. So let's say I have to draw it in such a way that it cuts the x-axis exactly 2 times, namely at the real values, negative 1, let's call this negative 1, and then 1, 2, 3. All right, so it cuts the graph through here and through there. It's going to open up because it's positive. And then let's have 3 turns, okay? You could have 3 turns or less. It doesn't really have to matter. But the maximum number of turns that it's going to have is 3. All right, so let's do it this way. How about we have it look something like this? So that's 1, 2. Let me draw that again. So I have, let's make the first 2 turns pretty soft. So what if I have something like this? 1, the first turn, 2, and then it goes through there, and then the third turn takes it right back up like this. Okay, so this is a possible graph. It doesn't have to be the exact answer. If you want to get the exact answer, you need to make a table of values and use intercepts and things of that nature. But this is a possible graph. It meets our description. It has 3 turns, 1, 2, 3, and it cuts the x-axis at exactly 2 points because we have only 2 real roots. So this is a possible graph for our solution. Okay, as indicated for us to find in part B. So there you have it. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel so you can get other cool clips, math clips such as this. And please post a comment to let me know what you think. Like this video if you liked it. And also share it with your friends via your respective social networking program. Thanks again for watching. More clips can be found on mathcoserve.com. Thank you.